here today going to talk something about the multi-scale modeling, and which will be different from your this software sessions or the software uses. So I hope that you will enjoy this session today. So let me share the screen first. So is the screen is visible to everyone?
Yes, sir, we can see it.
Okay. Okay, so thank you for inviting me for this session on the advanced analysis of the materials or the structures. So my talk is on the multi-scale modeling of the quasi-brittle materials. So I'll discuss about the introduction about the quasi-brittle materials and why this talk is important, or why this you can say the study is important, and then the methodology, how we can address the issues, and then some problems which we have addressed in recent past uh, with the help of our developed methodology. So let us start from the engineering materials. So when we talk about the engineering structure, so the most important thing which we will give as a solution, okay, as a designer we will give as a solution, that we will optimize the material and we will give a suitable material which can bear the stresses and strains which are going to come in the different structures at during its lifetime span. And also it must cope up the extreme events like earthquakes or high temperature loadings, okay, which are, you can say that which are generally their intensity is very high, and their time of occurrence is very less. So for such structure also, for such type of loading also, we need to design our structures. So let us come to the material, that how the material is behaved. The engineering material, if we study the engineering materials, then we classify broadly, we as an structural engineer or as a design engineer, we broadly classify our materials in two categories. So one is the ductile materials. Examples are alloys and metals. And another one is the elastic brittle materials, such as ceramics, glasses, and all other composites. So if we see the stress strain behavior for the ductile materials, so what we assume that fan material starts yielding, our structure fails. So we are not going to the other, you can say that the strain hindering regions of the ductile materials, but we only stops before the yielding starts. So if we see the behavior of these materials, so these materials are well understood in the behavior in past, and they have a lot of plastic deformation before the failure. So before they will fail, they will sag, and they will sag hugely, then they will give way. So we have enough time of, we can say that we can have enough warning before they fail. So then we will have very good safety margin factors for them, very less, and also well defined behavior which is understood by the researchers. And we also have the reserve strengths, which are the strain hindering reasons to cope up with the extreme events if they are passing the yield point also. Then also they have certain strength to bear it. In contrast, if we see the elastic brittle materials, so we have a linear stress strain curve and then a sudden catastrophic failure. So in contrast to the ductile materials, these materials can fail without prior warning. So there will be a sudden catastrophic failure. So what we do then, we want to avoid this catastrophic failure, so we impose much larger safety factors. So there is another class of material which is known as quasi-brittle material. So these materials are you can say the made up of the brittle links of different you can say that elastic brittle materials. So their stress strain behavior, if we will see, then they have a linear elastic slope, then near the peak they have non-linearity, and after the peak they have a descending slope. So we can say that they have a certain level of damage tolerance. So this damage tolerance is not accounted well in the literature, and there are inadequate understanding about the role of the damage tolerance due to the complex microstructure. They have the complex microstructure, and also the state of loading is also complex. So examples of these materials are concrete, which we widely, as a civil engineer, which we widely put on the structures. Then polygranular graphite, ceramic matrix composites, bones, geological materials such as rock, snow, etc. So there are variety of the, you can say, names are available there. So as we know that we don't understand this material well, so what we do that we superimpose or we impose the inappropriate safety margin factors, and we will say that these materials can be treated as an perfectly elastic brittle material. So the design results bulky, and you can say that it is not appropriate. So even if we see the behavior of these materials over the time, then as time ages, their microstructure have changes. So sometime their microstructure evolves and they will pick up the strengths. Sometime their microstructure dissolves and then they will have a, you can say, a reduction in the strengths with respect to the time. So that aspect is also not treated well and not understood well in the literature. So we try to address this, and our research is mostly focused on the method to develop to predict the performance and to evaluate the integrity of such structural components which are made of these quasi-brittle materials. So if we see, then what is the performance? So the performance or the parameters of the performance, especially the mechanical performance, are depends upon such as the elastic constant, the strength, and the damage evolution and propagation laws. So most of the quasi-brittle materials, they exhibit a hierarchy in their microstructure, and thus they can be approximated as the materials which are made of the brittle links which are interconnected at the different hierarchy of the length scale. So we will discuss in detail what I mean with the hierarchy in the length scale. So this overall property of these materials, if we see, then they are the function of the microstructure and the hierarchy. So we can say that if P is the performance in terms of E, S, and D, then that is the function of the microstructure characteristics and the hierarchy level within the material. So let us see the what is the hierarchy. So if we see the every engineering material, if we look into the material and if we zoom into the material microstructure, so it exhibits a heterogeneity at certain length scales. So these heterogeneity where the structures exhibits the heterogeneity, the length scales are known as the local length scales, and where we can consider these material as an homogeneous material, there the length scales are known as the global length scales. So so if we will see, so we have our research focus is mainly into the three type of materials: carbon-carbon composites, which are the ceramic matrix composites, then concrete, and the natural material like bones. So if we see the carbon-carbon composites, so if we see at the component scale, such as this is the nose tip of a propeller. Okay, so if we see here, our length of the components are in meters, and there the fluctuations or there the you can say the heterogeneities are in millimeters. So we can consider here this material is as an homogeneous and material. And if we zoom in the, or we will zoom in up to some millimeters, so we will come to know that these nose tips are made up of carbon fiber bundles which are embedded in the carbonaceous matrix. So this is termed as at that level the heterogeneous material. Okay, and we further zoom in the bundle. So fiber bundle is a combination of fibers and matrix, carbon matrix. So if we see here, our length scales are in micrometers. And if we further zoom in the matrix, so matrix also has a complex structure of the pyrocarbons. So at this level, our length scales are nanometers to few micrometers. So similar length scale hierarchy can be found in the concrete. If we see at the component level scale, so when we have component in the meters, so we can consider this as an homogeneous material, as our heterogeneity is at a very less level. It is in few millimeter level. But when we zoom in the concrete, then we will have the coarse aggregate which are embedded in the mortar. So at this level, if we want to check out the stresses or the distribution of the stresses, then material is heterogeneous. So, and if we further zoom in the mortar, then we all know that mortar is the mix of the fine aggregates plus the cement matrix. So cement as a matrix. So if we further zoom in the cement, so that is also a heterogeneous material, and it is made of hydrated and unhydrated particles of the cements plus the porous structure. So what we can derive from here, similar structure is also available in the bones, but we can derive here that at the different length scales, we have different microstructure of the hierarchical material, or we can say the quasi-brittle material. So their mechanical behavior, that is the stress strain behavior at the different length scale, is different. So the response is also different. So then this hierarchical microstructure combination can be expressed in the following variables, such as if we generalize these descriptions. So we can say the generalized description of the phase can be treated as an inclusion, which is embedded in the matrix. So there is definitely some inclusion which should be embedded in the surrounding matrix, or a winder, suitable winder. So, and interface between the winder and the inclusion, that is the third phase, which is also an important phase. Apart from this, if we will see, then we have the voids. At the different length scales, we have different voids. Means if we see the concrete at component scale, so we can see the void with the naked eyes. So they may be in the few millimeter in the ranges. But when we zoom in the material, and we will see at the micrometer scale, so the voids are also within the scales in the few micrometers to few nanometers. Okay. So at different length of scales, we have different type of voids. Means the diameter of the voids, and also different cracks which are present in these quasi-brittle materials. So these inherent defects, they are already present in the materials. Then we have random factors associated with their, you can say, with these faces, such as the shape of the faces. They are random, they are not perfect shapes. Then we have the size of the faces, that is also random. Then the distribution of the faces, means the location of the faces within our component, is also random. So it is randomly orientated. So some random factors are also associated with it. So if we see, then overall, if we see our material, then that is a hierarchical and complex microstructured material. So to define the behavior with the simple, you can say the strain relationship, and to predict the fracture behavior and its other qualities is not, you can say that, appropriate. So what we can say now here, our performance in terms of Young's modulus, strength and damage, is a function of now the geometry of the inclusions or the binders or the faces, then the material property of our you can say that different materials at the different length scales and the hierarchy of the length scale, at which length scale we are looking at. Suppose a crack is nucleating, so if it is nucleating at you can say the micro scale level, so we need to analyze the microstructure at that level. If it is nucleated and it is propagating at a higher level, so we need to analyze our stress strain relationships at that level. So likewise, we have to treat the crack at the different level scales, and then we can predict the life of these type of materials, or the components which are made of these kind of materials. So then we need here a mathematical model, so to define the behavior of these materials at different length scales. So these mathematical models or these techniques which bridges the gap between the two scales are known as a scale bridging techniques. And the technique which replaces the heterogeneous material with an equivalent and energized homogeneous material is known as homogenization. So what we do here, that we have a heterogeneous material, so we will load it, apply a load in on that material in a certain direction, and then we will measure the its strain energy. So let us that strain energy is pi h. Okay, so what we will do, that we replace this patch of material with an material, okay,
Sorry to interrupt
polycrystalline
you, sir.
material. Yes.
Yes, sir. Sir, are you sharing a window?
No, I'm sharing full.
Actually, sir, you might have shared a window when you were in Google Meet.
Okay.
That is why we are currently seeing only your title slide. If you could just
Okay,
go to
is
your
it?
Google Meet once.
Is it?
Now it is working now. Now it is on the
Okay,
costly
but
brittle materials. Yes, sir. Now it's
okay,
fine.
so now you are able to see it.
Yes, sir.
Okay, so
I
should I
think
go
it's
in this
fine, sir.
mode?
You can go ahead with this mode.
Okay. So this happens with when we are in online mode, so we don't know others, what others
Yes,
are
sir. Yes.
watching or what
Sir,
others are
right now we
listening.
are on slide number 7, right?
Okay.
Okay. Please
Yes.
continue, sir.
So what happens, that we replace this heterogeneous material with an equivalent homogenized material, means which has equivalent, means homogeneous material which has an equivalent strain energy under the set of the loading. So if pi h is equal to the pi e h, then we can say this homogeneous material is equivalent to our heterogeneous material, and we can replace it and we can model it, and then the properties or the analysis which we are carried out or which we are carrying are the correct one or the more appropriate. So how to do it? So there are different homogenization techniques or the scale bridging techniques, and the most you can say the simplest technique is rule of mixture. So then the other technique is Mori-Tanaka method, which is based on the Eshelway approaches. Then we have the asymptotic homogenization technique, computational homogenization technique, transform field approach, variational homogenization technique, etc. So I used to utilize the asymptotic homogenization technique. So we will talk about it. So what happens in the asymptotic homogenization technique, that we have a boundary value problem and we need to provide the solution for that boundary value problem. So let us, this is a heterogeneous material. So what we will do, that we will assume that this heterogeneous material is made up of a certain unit cell. That means there are certain replicability or the repeatability of the material in the all three directions. So if we have a unit cell which exists and we repeat that unit cell in all three directions, then we can you can say that we can make that heterogeneous material. So this is the one of the crude assumption of here we are going to make. And then the length scale between, that means the length of the unit cell and the whole domain is, means the difference between these two lengths is very large. Okay, such that xi, which tends towards the zero, which is the xi is the ratio between the global and the local length scales. That is the heterogeneous, which is the component, and the unit cell, which is replicating our heterogeneous structure. So the length scale difference between these two should be very, very large. So then if we look at the boundary value problem, so how we solve the boundary value problem? So there is a very simple method that we will take a differential equation, which is in terms of the, you can say that this is the stress equilibrium equation in terms of derivatives. So this is our first term, represents the equilibrium relations in terms of the derivatives. Then we have the boundary conditions in terms of the either you can say that displacement boundary conditions or the traction boundary conditions. So either we have the displacement boundary conditions, that means our nodes are, or our boundaries are fixed or hinged or roller kind of support they have, okay, or they have the loads on it. So the loads are counted as an traction. Okay, so then if we have this boundary value problem, then what we will do that we also have the constitutive relation between the two materials, means between the stress and strains for that material which are going to define here. Then we have the strain displacement relationship. And now if we choose any suitable function as a displacement function, so we can calculate the strains, and from the constitutive relation we can get the stresses. And when we put these stresses into the equilibrium equation, so we validate the nature of the laws, that is the mass momentum balance law. And then we can, if we apply the boundary conditions, so it will map to our, you can say, the problem exactly. Okay, so that we can do here. So what we assume here, that we assume a displacement function in terms of you can say that asymptotic expansion, and in the two scales, so two length scales. So x and y are the two different length scales. So x is, you can say that x is our local scale and y is our global scale. So if we have x and y, the two length scales, and we have a displacement function, so this displacement function we can put into the strain displacement relationships. So we can see that our strains are also expanding in asymptotic way. Okay, so if we consider the first three terms and then we utilize the constitutive relations, so we will see then our stresses will also expand in the asymptotic way. And then if we take these stresses and put into the equilibrium conditions and solve for the constitutive relations, so we will get these three equations. One is the minus scale, then current scale, and then next scale. So we have a term sigma ij in the power of -1, then 0, and then +1. So these three equations can be solved simultaneously, and then we can find out the result for it. So I'm not going through into the mathematics. This is very rigorous. So what we are going to use here, that if we solve these equations, so we will getting this constitutive relation. So this is the final homogenized constitutive relation which is derived from the local boundary value problem. Okay, so if we look at into this constitutive relation, then here we can say that this constitutive relation can be represented in terms of the special average of the different variables. So here variables are stresses, then our elastic constants and strains, and these are the thermal, you can say that uh, thermal coefficients. Okay, so if we see these special averaged variables, and if we have a unit cell problem, so we can define these special averaged quantities as an special volume average quantities. Okay, so these can be reduced to the volume average quantities, where we can define sigma ij is the volume average of the different, you can say, materials which are present in our heterogeneous material. And similarly, we can expand our stresses or the strains, okay, where we can model the jump between the you can say the displacements at the interface also, okay, by utilizing this approach. So how to solve it? So to make it more you can say that this analytical work, to make it more friendly, so what we will do that we will utilize the finite element scheme to have an approximate solution for this analytical expression. So what we will do that we will utilize the weak form of the local domain. So weak form of the local domain can be represented with the help of this equation. This equation can be discretized, can be written or rewritten in terms of the discretized function, okay, like this, in this equation where k into u is equal to re plus rq plus rv. Okay, so here k is our stiffness matrix, and this is the equivalent nodal load vector or the initial strains, and then the nodal vector for due to the surface forces, and then the nodal load vector due to the body forces. These are the combinations. So basically, we are solving ku is equal to f. So in finite element domain. So if we do it, so we need to provide also consider the periodicity of our unit cell. So remember that I said that we will consider our unit cell as an periodic element. That means if we repeat that unit cell in 3 directions, then it will reconstruct our material. So that means this unit cell is periodic in the nature. So if it is the periodic in the nature, so we can consider these 6 set of periodic boundary conditions and these 6 set of the loads. So these are our deformation modes and these are our boundary conditions. So if we consider one by one these load cases, so we can find out the you can say that the heterogeneous elastic constants for a material. So so if we can find out these heterogeneous elastic constant for material, so this technique is applied for concrete. So where we have reconstructed the representative volume element of the concrete using the X-ray tomography technique, and here you can see that these yellow grains in the 3D, you can say that cuboid. These yellow grains are the coarse aggregates, and this sky color you can face is known as mortar. And we have these blue color, you can say blue color patches. They are embedded whites, which are included in the directly included in the this our representative volume element through X-ray tomography. And we did all these we solved these all these three, you can say that 3-unit cells with the help of finite element method and asymptotic homogenization scheme, and we got this kind of you can say that the constitutive constants. So here we got you can say these upper matrix is the in plane, or the you can say that the extension matrix, and we have the shear terms in the lower diagonal. Okay, so we have also evaluated the you can say the ratio of the anisotropy, and for this concrete it is coming around 0.99. So this is very much, you can treat this material as an quasi isotropic material. So this, then further we have tested this technique on the microfibril. Here we have reconstructed we have considered the you can say the bone fibril, which is a combination of the mineral plates which are embedded in the microfibril matrix. So we have the different staggered and different arrangement of the microstructure of this fibril, and then we have established the elastic constants through our homogenization technique, and it falls very much you can say that near to the different datas which are you can say present in the literature. So the next problem which we have taken, that is of the fiber reinforced composite, Here these are the fibers which are embedded in this you can say the mortar or the slurry matrix, and where we have developed the relations for the E1, E2 and E3 of this composite, and we have determined the Poisson's ratios and the shear moduli. So here also the anisotropy is coming around the 0.9. So these three problems which we have addressed in recent past. So I acknowledge all the funding institutions which have funded my research, including IIT and University of Manchester, DST, IIT Delhi, National Institute of Technology, Hamirpur, and no, not the last for least. So I'm also nowadays addressing one more problem, that how this universe is created, and this is a very good problem, and it is also partially addressed in our literature. So if you also want to learn it, so you can join our program Learn Gita Live Gita at this website. So thank you for this. So I think I have finished my talk. So if you have any questions, so I welcome.